This video is the third in the lecture on cell balancing. We'll quantify how much balancing current is required to keep a battery pack balanced. We'll discuss compensating for cell self-discharge, unequal loads, and faults or defects. Conceptually, we want to assess and quantify the mechanisms causing imbalance, and then design the balancing circuit and its controls and the thermal packaging to support at least that much current. We'll do the analysis for a 200 amp hour battery. Why? Say we have a 10 kilowatt hour home energy storage battery, like a Tesla Powerwall. That's about 200 amp hours. Or an 80 kilowatt hour electric car, also 200 amp hours. Consider this an example of an analysis that you would customize and scale for your specific battery. Let's look at cell self-discharge. Cell self-discharge increases with temperature and is substantially higher at high state of charge than at low state of charge. This is kind of nice in that a nearly empty battery depletes itself more slowly than a fully charged battery. Here's a curve for one battery's self-discharge as a function of state of charge, and from the same source, an estimate of self-discharge with temperature. Let's do some math to get a sense of the size of currents we're talking about here. You might expect a larger battery to have proportionately larger self-discharge current than a smaller battery. So let's extrapolate the data we have here for a 2.4 amp hour battery to the 200 amp hour size of our target battery. Note that manufacturing quality and cell design matter, so in a real design, you should use data for the actual cell of interest. If a 2.4 amp hour cell self-discharges at 5 microamps at 80% state of charge, then a 200 amp hour battery may self-discharge at 417 microamps. Our worst case corner is at 100% state of charge and hot, say 45C, where we estimate the self-discharge to be about 7 milliamps. With regards to imbalance, what matters are differences in self-discharge, not the absolute value. For example, even with the worst case self-discharge, if all the cells are self-discharging equally, they will remain balanced. Imbalance comes from unequal self-discharge. For example, if one cell is self-discharging at 7 milliamps, while the rest are self-discharging at 6 milliamps, the pack is accruing 1 milliamp of imbalance. To estimate imbalance, then, we need to estimate the difference between the cells with the highest and lowest self-discharge rates. In this example, we'll do the analysis at the 100% state of charge, which is sensible for an electric vehicle which may rest at 100% for much of its time, plugged into a charger in the owner's garage. For an application like a stationary battery, which spends most of its time at some intermediate state of charge, we might do this analysis at 80%. Thermally managed battery packs will have some thermal gradient, perhaps cooler near the coolant inlet and warmer at the coolant outlet. For example, assume a 5 degrees C thermal gradient. This is about what I'd expect in a reasonably thermally managed battery pack. Since self-discharge roughly doubles for every 10 degrees centigrade, for a 5C gradient, we'll see 1.4 times as much self-discharge on the warm end of the battery than the cool end. So that's our answer, 2.4 milliamp imbalance. For this 200 amp hour battery pack, which spends most of its time near room temperature and is expected to experience a 5C thermal gradient, we can expect the pack to imbalance itself at a rate of 2.4 milliamps. Let's remember that number. Next, we'll consider the impact of unequal loads. Modern BMS chips are designed to have very equal input currents to minimize the imbalance caused by cell voltage measurement. For the BQ79616, for example, the measurement pin input currents are about 8 microamps, and guaranteed by the datasheet to differ by no more than 2 microamps. For the LTC6813, the typical input current is a mere 1 microamp, and so we should expect the channel-to-channel variation to be smaller than a microamp. For the latest chips, the variation in measurement pin input currents is so tiny as to be generally negligible. Unequal loads can be more significant when multiple chips are involved. Automotive battery packs typically incorporate so many cells in series that a single measurement chip isn't sufficient. In this scenario, mismatch between the chip's supply currents matters. Chip supply currents are much larger than measurement pin currents. For the LTC6813, the total power supply current is the sum of several currents of some milliamps each. When the chip is actively running, it consumes around 19 milliamps, with a possible variation of about 3 milliamps. About half that current powers the ADCs, and the other half is for the communications interface. The BQ79616 is similar, though the variation for the communications-related half of its supply current is not provided. Recall those datasheet supply currents. For both the chips we considered, the supply current was about 20 milliamps typical and 23 milliamps max, or in other words, 20 milliamps plus or minus 3 milliamps. That variation likely comes mostly from two sources, some due to temperature, and some due to manufacturing process variation. The temperature variation should be a small effect if the chips are all at the same temperature, as is likely for chips within a single battery pack. In practice, then, we might expect the supply current variation to be about half that 3 milliamps in the datasheet, around 1.5 milliamps. I will put 1.5 milliamps into our table. However, that's not a rigorous number. A conservative approach would stick with the 3 milliamps from the datasheet. Before we go on to faults and defects, let's discuss one caveat. There's one architecture decision that could increase the imbalance resulting from our analog front-end BMS chips beyond what we calculated. Imagine that the microcontroller queries the chips for their data. A common architecture has the chips in a daisy chain. Upon receiving a request for data, the first chip transmits its measurements, which doubles that chip's current consumption. Next, the second chip transmits its data, and the first chip passes it on to the microcontroller. Then, the third chip sends its data through the lower chips, and so on until all chips have transmitted their data. If we visualize that as plots of current consumption versus time, we might see something like this. Initially, everything is off, and the currents are near zero, some tens of microamps possibly. Then, the microcontroller transmits a short communication requesting chips to enter their active state, resulting in a power supply current blip. Now, the first chip transmits its data, with a corresponding current increase. Then, the second chip transmits its data, relayed by the first chip, with corresponding supply current increases for those two chips. Then, the last chip transmits its data, relayed consecutively by the other chips, with high supply current drawn by all chips. And the cycle repeats. The average current consumption for the three chips in this example are 12.5 milliamps, 15 milliamps, and 17.5 milliamps, which would cause a 5 milliamp imbalance between the groups of cells monitored by the top and bottom chips. The details will differ with the exact timing and number of chips, but this is a significant enough issue that many BMS chip suppliers offer an alternate architecture. An improved architecture entails a communications loop. The microcontroller can alternately talk to the measurement chips clockwise on one measurement cycle and counterclockwise on the next. This results in each chip transmitting the same amount of data when averaged over two successive cycles, and thus, nominally, the same current consumption for each chip. Let's remember that our 1.5 milliamps is a reasonable expectation only with a communications architecture ensuring that each chip communicates with a similar duty cycle. With that, let's move on to imbalance due to faults or defects. Imbalance due to faults or defects is tricky to quantify. How many cells leak depends on manufacturing quality, and often that is not truly known before manufacturing is in large-scale production. Also, determining what magnitude of internal fault to tolerate and indeed compensate for with balancing current, and when to say, uh-oh, that unit should be taken out, that's hard. So, to be honest, I don't have a rigorous recommendation for quantifying the allowable magnitude of leakage current due to manufacturing defects. This number heavily depends on the specific choice of cells and also the mechanical packaging and thus tolerance for one cell going into thermal runaway. So, what do we put for imbalance due to faults? In a perfect world, we'd use data. We'd look at the million units we already have in the field, look at patterns of atypical self-leakage and whether that precedes more catastrophic failure, and decide with knowledge. Without that, maybe we allow the same amount of balancing current for normal effects as to compensate for manufacturing defects. It's somewhat reasonable to allow our error budget to be of similar magnitude as our expected variation. With those numbers, we should design our balancing circuit and controls to compensate for at least 7.8 milliamps of imbalance. I'd recommend a little more. It's always good to have some design margin. Also, note that balancing may not be on continuously. If you only want to run balancing at night, say, a maximum of 8 hours per day, then the balancing circuit needs to support an instantaneous current 3 times the target we've calculated here. Take a moment to compare our calculated imbalance current to other currents around the battery pack. A car may see 1,500 amp peak current for a couple seconds. A typical continuous current may be 200 amps. For a 200 amp hour battery, 200 amps is a 1C rate. Even when the application load is not present, we may have a computer or microcontroller running, or possibly other peripheral loads. Tesla Sentry Mode uses the power-hungry autopilot computer, drawing perhaps 600 milliamps from the battery. Car headlights might pull 175 milliamps at the battery. A 1-watt microcontroller monitoring a home energy storage system might pull 20 milliamps from the 50-volt battery. Imbalance is really quite small relative to these other application currents. Here, I plotted the rough numbers that we estimated on a logarithmic scale. We're looking at different orders of magnitude. As we discuss balancing, keep in mind that balancing corrects for currents that are thousands or even a million times smaller than whatever the battery is powering. That was a lot, and we're done with the video quantifying imbalance in the cell balancing lecture. If you liked what you saw, please help this course get seen. Share it with a colleague, share it with a customer, share it with a favorite college professor, and then continue the cell balancing lecture in the next video.